Welcome back to AI Codecast, everyone. Ready for another deep dive?
Absolutely, let's do it.
Awesome. Today, we're tackling the happy number problem.
Oh yeah, this one's a classic. The name's kind of fun, but don't let that fool you.
Yeah, it can get pretty tricky. So, for those who haven't encountered it, what exactly is a happy number?
Well, you start with any positive integer, could be something like, oh, I don't know, 19.
Okay, 19, got it. What's next?
Then you square each digit and add them up. So for 19, that'd be 1 squared plus 9 squared,
Which gives us,
82.
okay, 82. And then,
You just keep doing that. Square the digits of 82, add those up, and see where you land.
and the goal is 2.
You either hit the number 1, which means you started with a happy number.
Okay. So 19, if you keep going, it actually does lead to 1, making 19 a happy number.
Exactly.
But what if you don't get to 1?
That's where those unhappy numbers come in. Instead of reaching 1, you get stuck in a loop, repeating the same numbers over and over again.
Like a mathematical merry-go-round?
Exactly. Never ending.
And so, like with the number 2.
Yeah, like 2, it'll just keep cycling forever.
So if we're writing code to solve this, we got to make sure it doesn't get trapped in those unhappy loops.
Right, that's
Yeah.
exactly where the challenge lies, yeah. How do you efficiently detect those loops so your code doesn't run forever on unhappy numbers?
So where do we even begin?
I'd say most folks would probably start with the brute force method.
Okay, so just follow the rules, square those digits, add them up, and see what we get. Do that till we hit 1 or realize we're stuck. It sounds simple enough, but I feel like there's got to be a catch.
You're right on the money. The problem is, with unhappy numbers, that brute force approach could run forever, right?
Not very helpful, to say the least. So we need a better way to detect those loops early on.
Exactly.
Any hints you can offer?
Well, think about it like this. How would you avoid walking in circles if you were lost in a forest?
I guess I'd try to leave markers, like breadcrumbs or something, to show where I've already been, so I don't keep going in circles.
Bingo. We need our algorithm to remember the numbers it's already seen.
Gotcha. So we don't keep recalculating the same things over and over again.
You got it. If we see the same number again, boom, we know we're in a loop.
Smart. So how do we actually do that in code? What tools can we use to create those breadcrumbs for our algorithm?
Well, luckily, there's this handy data structure called a hash set, or, set in Python, unordered set in C++A. You get the idea.
And a hash set is basically like,
Imagine a container specifically designed to store unique values and quickly check if something's already inside.
perfect for our breadcrumb trail. Before we get into the nitty-gritty of how to use a hash set, I think it's worth highlighting something you mentioned earlier, that efficiency in algorithms really matters. It's not just about getting the answer, it's about getting it quickly and cleanly.
Couldn't agree more. In real-world applications, if your code's inefficient, it can really bog things down. Slow programs, wasted resources, frustrated users, nobody wants that.
Right, so thinking about efficiency isn't just a theoretical computer science thing. It has real-world implications for making sure our software runs smoothly. And in this case, using a hash set is a perfect example of that. It can make a big difference.
Absolutely. But, all right, back to the hash set. So, how would we actually use it to crack this happy number problem?
All right, let's walk through the steps. So, first things first, we'd initialize an empty hash set, kind of like starting with a blank map of our number forest.
Perfect. Then we jump into a loop. This loop keeps running as long as 2 things are true. Our current number isn't 1, and it's not already in our hash set.
Okay, so the loop chugs along until we either find our happy ending or realize we're going in circles.
You got it. And inside the loop, we add our current number to the hash set, dropping a breadcrumb, so to speak.
Marking our territory.
Then we calculate the sum of the squares of the digits, just like we talked about earlier, update our current number to this new sum, and bam, we're on to the next number in the sequence.
Gotcha. Loop keeps going, checking the hash set, dropping more breadcrumbs, calculating, updating, and so on.
Right. And eventually, the loop's got to end. When it does, we've got 2 possibilities. 1, our current number is 1, which means...
We've found a happy number. Time to celebrate.
Exactly. But what if the number isn't 1 and it's already in our hash set?
Then we know we're stuck in a loop and the original number's unhappy. Case closed.
That's the gist of the hash set approach. But remember how you were asking about efficiency earlier? We'll get to that in a bit.
I'm already hooked on this hash set thing. It's like putting boundaries on our number forest, making sure we don't wander off forever.
You got it. Remembering where we've been turns a potential infinite search into a nice controlled exploration.
This whole cycle detection thing is pretty fascinating. Does this come up in other coding problems too?
Oh, absolutely. You see it all over the place. Like, imagine you're trying to spot loops in a linked list.
Oh yeah, those data structures. I can see how detecting cycles there would be important too.
Right.
We don't want our program getting stuck going around and around a linked list forever.
Exactly, and it doesn't stop there. Think about operating systems, where you need to avoid deadlocks. That's cycle detection in action too.
Wow, so this concept pops up in all sorts of unexpected places. I'm starting to realize how powerful these algorithms can be.
They are. But let's not get too sidetracked. Back to our happy numbers. So is there another way to tackle this problem besides the hash set method?
Hmm. You did mention something earlier about a tortoise and a hare.
Ah, you remembered. That's Floyd's cycle finding algorithm. And yeah, it's another really elegant way to solve this. It actually uses even less space than the hash set approach.
Ooh, even less space. Tell me more.
Imagine this. Two pointers, like runners on a track. We've got a slow and steady tortoise moving one step at a time.
Okay, got the tortoise.
And then there's the hare, the speedster, taking two steps at a time.
Okay, I'm picturing this race in my head. But how does this help us with happy numbers?
Well, here's the key. If there is a cycle, the hare, being faster, will eventually lap the tortoise inside that cycle. They'll end up at the same point on the track.
Ah, that makes sense. So if they meet, we know there's a cycle.
Exactly. And if the hare reaches the finish line, which for us is the number one, before meeting the tortoise, we know the number's happy.
Makes sense. It's like a little detective game happening in our code.
It is a really neat way to spot those cycles without needing a hash set.
Clever. Okay, so we've got the brute force method, the hash set method, and now this tortoise and hare algorithm. Any other tricks up your sleeve?
Well, there's one more approach that's kind of fun, but it's more of a shortcut. It uses a bit of a mathematical quirk of happy number.
Ooh, a shortcut. I'm all ears.
Get this, there's actually only one cycle in the whole happy number sequence. And it's not even that big, just these numbers.
Mhm.
4, 16, 37, 58, 89, 145, 42, and 20.
So every unhappy number will get caught in that same cycle.
Exactly.
So instead of keeping track of every number we see, we could just check if our number is one of those specific unhappy numbers.
Right. If it is, boom, we know it's unhappy.
That's a pretty neat trick. But it sounds kind of specific to this problem, right?
You're right. This hard-coded cycle approach wouldn't work for just any cycle detection problem. It really relies on the unique math behind happy numbers.
So it's like a special tool that works great for this specific job, but not necessarily a general purpose solution.
Exactly. But still, it's a fun example of how understanding the problem deeply can lead to some pretty cool optimizations.
Absolutely. Speaking of understanding the problem, what about those tricky edge cases? Things that might trip us up when we start coding this.
Ah, always got to watch out for those. One thing to consider is integer overflow.
Right, integer overflow. When those sums of squared digits get too big for our data types to handle.
Exactly. We might need to use larger data types or add some checks in our code to prevent things from going haywire.
So we're prepared to handle those really big numbers. What about negative numbers? Those aren't usually considered in the happy number definition, right?
Good point. We'd need to decide how we want our code to behave with negative input. Do we treat them as unhappy right away, or do we take their absolute value and then proceed?
It's like setting ground rules for our code, making sure it's consistent and predictable.
Exactly.
Well, I think we've laid a great foundation for understanding this problem. We've talked about the basics of happy numbers, explored those different approaches, and even touched on some potential pitfalls.
I'd say we're ready to dive into the code.
Absolutely.
Welcome back. Now it's time to get into the nitty-gritty of these happy number solutions.
Right. We've got our map laid out. Now, which path do we take first?
Let's start with the hash set approach. It's a really good balance of clear and efficient.
Sounds good. I'm ready to see how those breadcrumbs actually work in code.
Okay, so let's say we're writing a function called iIsHappy. Takes an integer, spits out true if it's happy, false otherwise.
Gotcha. The main function, our happy number checker.
Right. And inside that function, the first thing we do is create a hash set. We'll call it scene.
To store those breadcrumbs, right?
I got it. Now we set up a loop. This loop keeps going as long as our number isn't 1 and it's not already in scene.
So, until we hit that happy number, or we realize we're stuck in a loop.
Exactly. And inside the loop, what do? Well, first, we add our current number to scene.
Dropping that breadcrumb, marking our territory.
Now we calculate the sum of the squares of the digits, just like we talked about.
And we update our number to this new sum, moving on to the next step in the sequence.
Perfect. Loop goes round and round, adding breadcrumbs, calculating, updating, and eventually, oh, the loop ends. Now we've got two scenarios.
Either our number is 1, meaning we found a happy number, or
Or it's not one, but it's already in scene, meaning
we're in a cycle and it's an unhappy number.
bingo. That's the heart of the hash set method. Now, remember you asked about efficiency?
Oh, yeah. You mentioned big O notation. What's that all about? I think some of our listeners might be scratching their heads.
Good point. So big O notation, it's basically a way for us to describe how the performance of an algorithm changes as the input gets bigger. Like, does it slow down a lot or just a little?
So instead of just saying this algorithm is fast or slow, we can be more precise.
Yeah. And it helps us compare different algorithms.
Makes sense.
So for our hash set approach, the time complexity is what we call O log n,
Yeah.
where n is our input number.
O log n. Huh. Can you break that down a bit? What does that actually mean?
Right, imagine you're looking for a name in a giant phone book.
Okay, got my phone book.
You could go page by page, right, but that would take forever. A faster way is to open the book in the middle, see if the name's before or after that point, then keep dividing the book in half until you find it.
Divide and conquer.
Exactly. And that's kind of what's happening with the hash set approach. The number of digits we're dealing with, it gets smaller with each step.
So the problem shrinks down quickly.
You got it. That's why it's O log n. Even for big numbers, the number of steps our algorithm takes grows much slower than the number itself.
So we're taking those shortcuts, not checking every single possibility. Makes sense. What about the space complexity? Does the hash set get huge as we add more breadcrumbs?
Well, good news. The space complexity is also O log n because we're only storing the unique numbers, not every single one.
So we're efficient with both time and space. I'm starting to see why this hash set approach is so popular for cycle detection.
It's a great tool. All right, ready to move on to Floyd's cycle finding algorithm, the tortoise and hare one.
Absolutely. You got me hooked with that analogy. Bring on the tortoises and hares.
All right, so picture this. Our main function is happy is still there, but instead of a hash set, now we've got two integer variables. We'll call them slow and fast.
Our racing duo.
Right. And remember our helper function from before, get next number, to calculate the next number in the sequence.
Yep, got it. What do we do with our tortoise and hare?
We start them both off at the same spot, equal to our input number.
Okay. The race begins.
Now, here's the clever part. We're in a loop, and it keeps going as long as slow and fast are pointing to different numbers.
Until they collide.
Exactly. Inside the loop, we do two things. First, we move slow one step forward using our getNextNumber function.
The tortoise takes a slow and steady step.
And fast, being the hare, takes two steps forward. Two calls to getNextNumber.
So the hare is zooming ahead.
Right. Now, at each step, we got to check a couple things. One, if fast hits 1, we know the number's happy and we're done.
The hare crossed the finish line.
Exactly. But what if slow and fast become equal?
Mid-race collision. What does that mean?
It means we've got a cycle and the original number is unhappy. We return false.
Gotcha. So if neither of those happens, the loop finishes, and if fast hit 1, we know it's a happy number.
Exactly. Floyd's algorithm in action. Pretty cool, huh?
Very cool.
Yeah.
So both the hash set and Floyd's algorithm, they have that O log n time complexity, but you said Floyd's uses even less space.
Yep. That's because the hash set, it stores all those unique numbers, which can add up. But Floyd's algorithm, it just needs those 2 pointers, slow and fast. That's it.
So even though they both take a similar number of steps, Floyd's is more memory efficient.
You got it. It's all about trade-offs sometimes. But Floyd's is pretty neat efficient with time and space.
Impressive. Okay, I'm ready to hear about that hard-coded cycle trick. It seems so different from the other two approaches.
You're right, it is. And it shows how understanding the math behind a problem can lead to some really cool solutions.
All right, how does it work in code?
So our isHappy function is still there. But this time, no hash set, no pointers. We've just got a loop that keeps running as long as our number isn't 1.
Still looking for that happy ending.
Right. But inside this loop, we do something special. We check if our number is one of those specific unhappy numbers from that one and only cycle. 4, 16, 37, you know the drill.
So instead of remembering all the numbers we've seen, we're just checking against this list of known unhappy numbers.
If it matches, boom, we know it's unhappy. Return false. If it's not on the list, we just calculate the next number in the sequence and go again.
And if we hit 1, well, we're happy.
Exactly. Simple as that. But like we said, this one's very specific to happy numbers. Wouldn't work for just any cycle detection problem.
It's like a specialized tool, right?
Yeah.
Super effective for this one job, but not very versatile.
Yep. Still, it's pretty cool, and it shows that sometimes understanding a problem really deeply can lead to some nice optimizations.
Absolutely. This has been an awesome exploration of the happy number problem. We've covered different approaches, talked about cycle detection, big O notation, even edge cases.
And there's even more to explore.
Oh, like what?
Well, what if instead of just one number, we wanted to find all the happy numbers within a certain range, like all the happy numbers between 1 and 100?
Whoa, that's a cool twist, taking it to the next level. But wouldn't that mean checking each number one by one?
It might seem that way, but remember what we talked about. If a number is happy, all the numbers in its sequence are happy too.
Right, those happy little families.
So maybe there's a way to use that to our advantage. Like if we find one happy number, we could mark its whole sequence as happy. Save us some work.
So we wouldn't have to calculate them all individually.
Exactly. But we need a way to keep track of all those happy families, maybe using another data structure.
Another hash set, maybe, to store the happy numbers we've already found.
You're on the right track. It's like building a happy number lookup table as we go, caching those results so we don't repeat the same calculation.
Love it. It's like building a map of happiness in our number world. This is amazing. Who knew that happy numbers could be so deep?
It's been a fun ride, and maybe it's a good spot to take a breather.
Yeah, let's give everyone a chance to digest all this and maybe try some of these ideas out. We'll be back soon to wrap things up. And we're back, ready to wrap up our happy number adventure.
Absolutely. It's been quite a journey.
Before the break, we were talking about finding all the happy numbers in a range, not just one. And I think we were onto something with using another hash set to keep track of them.
Yeah, that's a good way to go, like building a little happy number dictionary. So as we go through our range, checking each number.
We first see if it's already in our happy dictionary.
Exactly. If it is, boom, we know it's happy. No need to calculate anything.
But if it's not in the dictionary, then we got to figure out if it deserves a spot in that happy club.
And if it is happy, we add it to the dictionary plus all the other numbers in its happy little family.
So if we run into any of those later, we instantly know they're happy too. No need to recalculate.
Exactly. It's like building a whole network of happy numbers.
Super efficient, especially if we're dealing with a lot of numbers. We're basically caching those results, saving ourselves a ton of work.
Right. A little bit of cleverness goes a long way.
I love how this optimization really uses those special properties of happy numbers to make our code smarter.
It's a great example of how understanding a problem deeply can lead to some really elegant solutions.
This whole deep dive has been amazing. We've gone from the basics of happy numbers to all sorts of cool algorithms, optimizations, even edge cases.
It's been a blast exploring all this with you.
I hope our listeners have enjoyed it too. Who knew happy numbers could be so fascinating?
It just goes to show even a seemingly simple problem can lead you down some pretty amazing paths in computer science.
Absolutely. So to everyone listening, keep those coding brains working and never stop exploring.
And until next time, may all your numbers be happy ones.
Thanks for joining us on AI Codecast.